AI processes information differently than we do. When we read a sentence, we understand its meaning almost instantly. We connect words to ideas, to emotions and intention. But when AI receives that same sentence, it doesn't experience language the way a human does. So, what does AI really see when we prompt a question into it? The answer begins with tokens. Tokens are the units AI uses to process information. They are the pieces between human language and machine computation. And once you start to understand tokens, a lot of AI becomes much more easier to understand. You'll start to understand costs, speed, context windows, and even why some models feel more capable than the others. So, what exactly is a token? In simple terms, a token is a chunk of data a model can work with. Uh, if we're talking about the text, it could be a word, it could be a part of the word, or it could be a punctuation, or even it could be a space between two words in the sentence. So AI does not always see language a word by word as we do. So let's make that visible with an example. Let's take a simple sentence. AI does not read like we do. All right. And when I read this sentence, I understand the idea almost immediately. I do not think about coordinates, index, or vectors. I just understand the meaning. But a language model begins in a very different way. Before it can respond to the sentence, it first breaks this sentence into smaller pieces called tokens. So instead of treating this as one complete sentence, the model may see something more like this. So here you can see it highlighted with different colors. Here we can see the number of tokens, which is 8 from 28 characters here. And actually this number could differ from the model to model. Here we can see same, but for example, for more legacy model, GPT-3, we can see that AI got split into two different tokens. And this detail really matters because a token is not always a full word. It could be a part of the word, like here, and it could be a punctuation, like here, this dot in the end of the sentence. So at this point, the model is no longer dealing with the sentence the way we do. It's dealing with sequence of structured pieces. The next step is that tokenizer looks up each of these tokens in the model's vocabulary and replaces each of them with a numerical ID. So we can see it here. These numbers are not meaning by themselves. They are just identifiers, and you can think of them like entries in a giant dictionary inside the model. So model just uses these numerical representations to identify the exact token in its big vocabulary. So now this sentence has become a sequence of the numbers, a sequence of token IDs. But that's still not enough, because if I tell you that token read has an ID of 1100, that number alone does not tell the model what read actually means and how it is used or how it relates to other tokens, like, for example, book or write. And that's where embeddings come in. An embedding is the learned vector attached to that ID. So instead of 1100, it is a list of many numbers that gives a token a position in high dimensional space. So you can think of this vector as a system of coordinates which places this word in the mathematical space. So let me make it more visible with the example. Let us type just same sentence. Okay. I will hit generate to see how it processes. For this demonstration purposes, it uses the GPT-2 model. I mean, it's not the latest one. It's pretty small, which has only 124 million parameters, but the principle of the transformer architecture is same. So it's, from my perspective, it's enough for these demonstration purposes to understand how these embeddings and vectors work under the hood. So here we can see our input, how it was split into tokens. Then we have this ID we discussed. And here we could see these pre-learned vectors. The vector is what helps the model represent relationships, usage patterns, and the context in which token appears. So tokens used in similar contexts tend to get more similar embeddings. And they basically will be closer in this mathematical space. They will have more similar coordinates. So now imagine placing a read somewhere on that coordinate system, and this is a high-dimensional mathematical space where the LLM stores all its tokens, right? So here we can see it has 200 dimensions, and here we have all the vocabulary LLM knows. So let us search read word. Here we can see the most related words. We can isolate them and see how this read word relates to the most close in terms of sense to the most related words in the LLM's vocabulary. So this actually does not mean that model understands these words the way a human does. What it means is that it has learned useful mathematical relationships between them. And how does it learn those relationships? So over time, tokens that appear in similar context begin to develop more useful and more similar vector representation. So that is essentially what we can see here. In other words, the model gradually builds a mathematical map of language. And that is the idea. It works with mathematical relationships between token representations. So once those embeddings are in place, the transformer can process them. Now, up to this point, we have been talking mostly about text, but this idea actually goes much further. So tokens are not just for language, they are a broader idea, turning complex raw data into structured pieces a model can handle mathematically. That is why they are really important. They connect a human input with the math inside the model. Different models can use different tokenizers and different vocabularies, and exact token counts may differ from model to model, and the same task could actually require different token budget. So the same idea may require different amount of tokens depending on the model. One of the most important concepts related to tokens is the context window, which is amount of tokenized information a model can work with at one time. So let me show you. I'm going to be using Cloud Code documentation because it has a really nice visualization of context window. And first, let's start the session. And we can also see that context window normally includes not only prompt itself, but also it includes earlier messages, instructions, documents. So here we can see, for example, system prompt, which costs 4K tokens, right? And even before I type prompt, it loads already before, and it already impacts the final cost. Now let's send the prompt. Here we can see that it costs only 45 tokens. And here is the output produced by the model. And we can also see that it actually eats our context window. So everything here impacts the final price. And that has direct consequences for usability. A larger context window can help with larger conversations, larger documents, transcripts, and bigger code base. And a smaller one may force the model to lose track of earlier information more quickly. So tokens are really important in terms of pricing, because many AI systems price, I would say all AI systems price usage based on how many input and output tokens you use. Once again, here our context window. We already used almost 20k tokens by only pasting 2 simple prompts here. Because our model has big context, we loaded already system prompt, we added some skills. Let's assume that it's our agent. It has some context, it has some MCP tools, and on each follow-up request or even small prompt, the model will be tokenizing its context. So the next time you type a prompt into AI system, just remember that it doesn't read the message the way we do. It splits it into some tokens, and when you understand how it works, you can optimize your costs, and you can actually communicate with your model more efficiently. Thank you for watching this. Bye bye.